Okay, so, got information, we showed this. Got two ramps, roll a ball down each one, 60-centimeter ramps. Ball one rolls down the incline in 60 centimeters from rest in 4 seconds. And the ramps are straight, so we have a constant slope, which should give us a constant acceleration. Okay? Ball two rolls down identical, yeah, I guess I got all the letters now, identical incline with a different slope in 2.5 seconds. Okay? So, start asking questions. Where in the incline should ball one be placed so it reaches the end of its incline at the same time as ball two? And another one, where should ball two be placed so they reach the end with the same velocity? Okay? Well, everybody started thinking about the questions. Nobody thought about given information, okay, in any way that was going to work, okay? Although I think you would have. But you're so busy thinking about the question, you didn't see what you're given, okay? So a big principle in solving problems you're going to need on the test, because I made up a beauty, okay? Figure out what you can do with the given information before you worry about the question. You got a huge amount of information here. So when I posed that to you, you said, well, you can start with acceleration, start integrating, okay? Now before you were talking about, well, you know, displacement and time interval and all that stuff, which is also good, okay? But maybe we want to focus on, okay, so if we start from uniform acceleration, we know if we have enough information, we can find our x1 of t, v1 of t, x2 of t, v2 of t functions. Right? So, we know we can do this. Okay, the things you mentioned. We could start with the integration. We get the two equations for x1 of t and x2 of t, put in our initial conditions, we get simultaneous equations. Or we know it's uniform acceleration. We know how to derive 4 equations for uniform acceleration using calculus or just using the v versus t trapezoid and labeling it total. Okay? And we get the 4 equations that we use for uniformly accelerated motion, knowing that if we know any 3 of initial velocity, final velocity, acceleration, displacement, time interval, we can find the other 2. And we do have that for each ball. So, okay, so, you know, without necessarily diving into the details, it's a matter of taste whether you dive into the details. I don't think it's a good idea to dive into the details unless you know where you're going. If you can't figure out where in the heck you're going, dive into the details and then see what you can get from that, right? So, but if you see this, it gives you a structure to the problem. Now, if you dive into the details, I'm pretty sure both of you will be able to get this, okay? Pretty sure. Because I've seen you do pretty good work on this, okay? Not sure, some later stuff.
Seeing the numbers makes it a lot easier than when you ask.
Yeah, but you want to abstract it to the, yeah, I mean, you want to see what you're going to do with the numbers. You know that you can get a position and a velocity function for each ball, right? Okay? So all I'm doing here is writing down the fact that you know you get the position and velocity functions. But it helps to call one x1 of t, the other v1 of t, and so forth. Okay? Not big on numbers too, so yeah, that's okay. But I'm kind of advocating for get an overview before you dive into the numbers. Because you can end up getting lost even if you've got an overview, you know where you're headed. Okay? Now, if you get into the numbers and have good instinct for where you're going, especially in a problem like this, which is not all that hard, okay? You're okay, but you say, oh, yeah. Not sure you're going to see what to do with the numbers, but let's say now that you've got your functions, okay? Again, I'm reasonably confident that you would get the two functions, okay? What would you do with those two functions? Actually, four functions. I mean, two functions for each. But if you know the position function, of course, the velocity function is just what's in here. So, okay, so assuming you got them, what do you do with that?
You can just plug in the information we have to find the answers to both those questions.
Eventually set up.
Somebody being loud out in the hall, not all that loud, but given my hearing loss, gonna have to say it just a little louder.
After plugging everything in, you'd set some of those functions equal to each other, the position and velocity functions.
Okay, well, you can always do that. Okay?
Compare them to each other.
So, okay, well, let's take the first question here. We want to look where ball one should be placed so it reaches the end of its incline at the same time as ball two. And we know the functions for ball one and ball two, at least for my demonstration, right? Okay? Okay, well, what's the first thing you might want to do?
Write down your information, your variables.
Well,
Name
assume
everything.
assume you solved this part of the problem. Just breaking the problem down into chunks, right? We've got position and velocity functions for that situation, okay? How would you use one or more of those functions to get some information that you're going to need?
You can plug in the information you already have.
We use the information we already have to find these functions, right? So plugging in the information we already have would tell us what we already know. What's different about this situation than this one?
Ball one isn't placed at the top of the ramp. Yeah, the time.
Yeah, why not?
As John said, the time is different as well. And that's,
Yeah, well, time is different, so you want the time to be the same.
Mm-hmm.
Okay. So must be dead. Good. Oh, I'll turn it on. Good reason. Okay. Okay, talk about time. Is there something you can find about time?
Velocity and average acceleration.
Well, we'll already have found that. In the process of finding these functions, we will already have found that. Okay?
you can plug the change in time into the position function.
What change in time? In which
Change
position function?
You can plug the amount of time that for ball one, you plug in 2.5 seconds because it's supposed to reach the end of the ramp at the same amount of time the other ball reached. You can plug in 2.5 seconds into ball one's position function because you know where the final position is.
Okay,
Find
so-
the initial.
Okay, so that's one of 2.5 seconds. Well, ball 2 travels the length of the ramp, right? So,
You can use that to figure out how far up the ramp it needs to be placed.
yeah, so that's how far up the ramp you gotta be. Okay? Now find an x1 of t, b1 of t, x2 of t, b2 of t is a straightforward calculation. I'm not going to go over because you know how to do that. And if you don't, make sure you do, but I've seen you do enough on problems of this nature that I don't have any question that with reasonable review, which you probably don't even need. You can probably muddle your way through it right now. Try to get to where you don't have to muddle because that gets confusing on a test, right? Okay? Okay, so good. And how would you answer this?
You do the same thing with the velocity function.
Okay, more specific?
Maybe go back in.
You set their velocity functions equal to each other. Well, not quite.
Yeah, they never will be. Because these functions, this velocity is always going to be less than this one, except at the x equals 0.
Well, you plug in the data you have to figure out what the final velocity is of the first ball, and then you set that velocity equal to the other ball's velocity function.
Yeah, makes sense. Well, you kind of want to see that before you start, if possible. You see this situation, you say, okay, well, then I'm going to get the velocity function. Okay, then have this function. Maybe you write it down a little bit so you got something to look at. And say, oh, done. All I got to do is get these functions, and there's two simple things to do, okay? And one of them is this, the other is exactly what you said, okay? That would be V2 of T. Set it equal to V1 in 4 seconds, right? Okay. Solve for T. Well, that still doesn't tell you where you should put the ball, does it?
No, but if you plug in that t into the position function, it will.
Okay. So I'm going to say call the solution T2 Bx2 of T2 from the M, right? You understand how being able to write this out can be helpful when you're trying to solve a complex problem, okay? Working through the numbers and understanding what each number tells you is also helpful. If you got both alternatives, you're going to be able to solve more challenging problems. One of the things we develop in the course, actually the main thing I think is problem-solving ability, okay? And especially ability to relate a problem to something you've got in front of you. Not just some words in the textbook where you see certain key words and plug into some formula, okay? But understanding where the formulas come from, what you do, okay? How to derive them, which I hope you do, okay? In some cases, the formulas are too complex, you can't derive them. That's not true of anything we've done so far. Okay? Okay, so there we have it. Okay, that's pretty good.